Hey guys, welcome to this video. After a long period of time, I finally got the time to post this video, and it's on the topic, as you can see, Introduction to Quantum Mechanics, and it's a really interesting subject. And guys, this is also to tell you that I'm taking reference from the book Quantum Mechanics, the Theoretical Minimum. It's a really good book to read, and it is written by the esteemed physicist Leonard Susskind and Art Friedman. This is a really good book, and you can buy this book from the link given in the description box. So let's get started without wasting any time. So first of all, to understand quantum mechanics, we need to start with an experiment. It's not a practical experiment, we'll imagine it. Okay. So what we have to imagine? We have to imagine that we have an apparatus A which measures the state of a particle being oriented along the z-axis to be +1 or -1. Now for the time being, let us consider the result of the measurement to be +1 along z-axis. And you are satisfied that the result of the particle is +1 after measuring the state of the particle several times with the same apparatus A. Now let me tell you about the apparatus A. It's an apparatus which interacts with the spin of the particle and shows a number on its surface which is either +1 or -1. And till here we couldn't see any difference between classical or quantum mechanics. So we'll discover that in the next section of the video. But now let's come to the point. Make the apparatus oriented along x-axis. The result will be +1 or -1, but that's not the point that is to be emphasized. Now again rotate the apparatus towards z-axis and measure the spin. This is the main task that we are going to do. We need to disturb this +1 state along z-axis and rotate it along x-axis, and again return to z-axis and measure the spin. Now according to classical physics, there should not be any change of the +1 spin state along z-axis. But quantum mechanics makes a big deal out of it. It states that the second measurement is equally likely to be +1 or -1. That means there are equal probabilities of 50% of the state being +1 or -1 along the z-axis after the disturbance given during the measurement of the spin along x-axis. This is where we find the difference between classical mechanics and quantum mechanics. And this concludes that making a measurement of a quantum object in a system changes its state in some other system. Means while we are measuring a quantum object in a system or with respect to a system, it changes something in some other state or other system. So that's a very crucial principle of quantum mechanics, and let us continue with the topic quantum propositions. Now let's consider the following pair of sets in case of a die where the sample space is 1, 2, 3, 4, 5 or 6, any one of them. So I think the viewers will know about sample space. It's the total or the sum up of all the possible outcomes of an event. And let us see what are the sets. The sets are that A is a set that shows the proposition that the die shows a number less than 4. That means the favorable outcomes can be 1, 2 or 3. And B is a set that tells or that shows the proposition that the die shows an odd number. The favorable outcomes will be 1, 3 or 5. And the number of favorable outcomes is 3. And Now consider the propositions which is made up of the sets A and B, and we'll test whether they're true or not using the dice. What are they? Let us take a look on them. They are A or B and A and B. Okay, these are the two propositions that we are going to talk about, and we need to put on some axioms to define these propositions, and these are related to the set logic of classical physics, which is also called Boolean logic. So let us see what are the axioms that we need to define the propositions A or B and A and B. So the first axiom that we need to define is for A or B, and this proposition is only true when the die shows either A or B or both inclusive. That means the favorable outcomes are 1, 2, 3 and 5. And the axiom that defines the proposition A and B is only true when the dice shows a number that satisfies both A and B. That is, the favorable outcomes are 1 and 3, which is odd numbers less than 4. And these axioms can remind you of the logic of sets in classical physics, which is also known as Boolean logic. And if you observe carefully, that we can find the propositions A and B are A are the same. Precisely, the truth of proposition A and B corresponds to the truth of proposition B and A. Same is the case for A or B and B or A. But now let's come back to our quantum world and consider the sets A, which states that the particle is in a state of positive 1 along the z-axis, and B, which defines that the particle is in a state of negative 1 along the x-axis. Now let us test the truth of these propositions. And I should also mention that the same axioms are applied here. Now let's test the proposition A and B and A or B after changing the sets from classical physics to quantum physics. Now at initial state we know nothing about the spin and will measure it very innocently without knowing anything. Suppose we measure the particle along z-axis and get the spin state plus positive 1. It proves that the proposition A or B is true. Yet, let's measure the spin along x-axis just to know the truth of the proposition A and B. According to what we know still now in quantum mechanics, that the spin can equally be plus 1 or minus 1 along the x-axis. Now let us test the proposition B or A knowing that A or B is true. We find that the state of the spin to be plus 1 along the x-axis for the time being. This is just an imagination. Due to the measurement made along x-axis, the previous spin state of positive 1 along z-axis has been disturbed. That is, now the spin can be equally positive 1 or negative 1 along the z-axis, making the truth of B or A undetermined. The experiment concludes that the truth of A or B has nothing to do with B or A, or vice versa. So in case we find any proposition like a particle P has a momentum V at a time t, a particle P has a position at time t, has no meaning in quantum mechanics. Precisely, quantum mechanics is a quite indeterminate section of physics as compared to classical physics. And in classical physics, we always see that things become determined. Everything becomes deterministic, but our nature doesn't work like that. So hope you liked the video. If you want, you can download the PDF of this presentation from the description box. And also, to remain updated, please do press the subscribe button, because in the next video I'm going to cover the required abstract mathematics for quantum mechanics. Thank you. Hope you liked the video. Please support our channel.